Yeah, so there's a lot of slides. So as last time, I'm not going to go through like in detail about this. So I'm going to just go quickly through them and just let me know, stop me, and then if you have any questions or comments, just ask or say something.
Someone has mentioned in the chat that they weren't able to run the labs either.
Yeah, yeah. It's a shame because they show, although even in the videos they only show those very, very quickly. So
I see.
yeah, we would need to we need some more time. I need some more time to do it. It's it's a lot, I think. But let me so in this testing deployment, they cover the right-hand side of the picture when they have the deployment maybe session. So this is the kind of the big picture of all what they show as what kind of testing is available. So like when you train your model, you have your training system tests, the validation tests, the functionality tests when you test on the on a few important examples. So the kind of like the training tests can take like even overnight. The validation test can take like an hours, and then functionality tests like minutes. And then once you deploy the model to production, you kind of monitor that for downtime, for errors, and stuff like that. So this was the kind of the big picture of the lesson, and then they went through details about that. They showed some paper from the same guys that released the first paper on the ML ecosystem. Yeah, that was the one. So also they compared like the traditional. What I'm going to do, I'm going to mute all, and then
Sure.
if anyone wants to unmute themselves, let me mute all. So if you want to talk, just unmute yourself.
Now you muted yourself, Michael, so you have to unmute yourself.
Yeah, so my system I wasn't able to make one of my systems to work, so I connected from a laptop. So now I have two computers, so good point. So I muted everyone on the hosting of the computer that started the meetup. So now I had to unmute myself from the other one. Okay. Thank you. Thanks for letting me know. Yeah, so what I was talking about, they showed that difference between like traditional software engineering when you have like code and then you have your running system, so you have to test it. Where in the machine learning we have all data and model training. That's kind of bigger difference and what makes the whole thing a little bit more complicated. So that was the kind of key point for me from those slides. And then they list all sorts of different tests when they even go in details in the videos. So I'm not going to spend too much time on it either. But they again show that we have tests connected to data, tests that are related to our model. The tests are linked to our model machine learning infrastructure, and then the tests that we can run when our system is in production, so monitoring tests. And they did some survey that was quite interesting. I think that was from Google. They've assigned like a couple of points for each of the tests that they do at Google, and then they did. So the 5 points was maximum. So you could get like 5 or more points, and that was very good. And then they did that survey at Google when they use a lot of like they interviewed 36 teams of the machine learning at Google, and the average score was like 0.5. So that bigger picture is like very ambitional at the moment, so like a target, but we're not there yet. But I think that was the key point. And then I think they moved to deployment. Right. So also they showed like this continuous integration tools that could be used together with Docker. So like a couple of them is like Circle CI or Travis or Jenkins. This is kind of the tools that's available. In the labs, they use Circle CI. So these are the tools that can run tests on your code automatically, so you don't have to do that. So you push some code to your GitHub repository, and then you get the green or yellow or red labels saying that your test passed or failed. So it's kind of automated way of testing your code. And they also mentioned some good things about this build guide thing, that more and more people are using it, although I'm not sure exactly how this works. They didn't even explain that in the videos. So then they were talking about Dockers a little bit. They showed what's the difference between the virtual machine and then the container like Docker. So the Docker is, there is no operating system, so it's lighter. And more people are switching to Dockers. And then you can, so they showed also how you can configure a Docker, like a Docker file. They showed some Docker ecosystem you can build, pull, and run. There is this Docker Hub thing that you can, something like a GitHub for codes. It's like for the Docker files. So you can get some Dockers from there and submit your own Dockers there. And they showed this nice graphic that shows that it's used more and more, like going from 1 billion in 2015-ish to now about 12 billion 2017. So it's used more and more. And then you can use systems like Kubernetes to orchestrate your containers, so you can scale up your application. Depends on the usage. So you don't have to pay for like 10 virtual machines, regardless if they work or not. So Kubernetes would kind of scale it up dynamically. If you have 10 users, it will be very small. If the user base grows like 10,000, it will automatically create more nodes for your system. And then they showed how to deploy that on the web. And they talked about the REST API and some other options, how to deploy to VMs, scale using containers, and also using the serverless function like AWS Lambda, for example. Yeah, so once you train your model and you have your weights, you put those weights somewhere to a serving system, and then you scale it to demand. And there are many different ways to do that. And there are some tests you could do on those as well. I'm going to scroll through that. So something they don't recommend is to deploy your code to like your own infrastructure, your own computer. Something better is to deploy the code to the cloud instances, and maybe even better to deploy Docker containers to the cloud instances. So that's what at least that's what they show. And then you can use Kubernetes. It's a Google open source to manage your containers. You can also do serverless. So this is service like from Amazon or Google that you don't have to care about how many virtual machines you have and so on and so on. So that system would make sure that you have enough resources to run your code if your user base grows. And it's not that expensive as well. You pay like 3 cents per one request, I think. So you can have a lot of requests, and you get a lot of requests free as well. So Lambda could be a good option to do. And you only pay for what you use, so you don't have to pay if you don't use that. So that's also quite interesting. Yeah.
Michael, maybe a question from the chat.
Yeah.
So Sagar is asking if anyone has any experience with Mesos. In the lectures, they were stating people using Mesos and it's recommended, and he hasn't had the chance to check it out yet.
Which service?
Mesos, MESOS.
Right.
So
I didn't know. No. I don't know that one.
Okay.
Anyone else?
Anyone? Nitin mentions they use Kubernetes for work.
Yeah.
for deployment of web apps.
Yeah. Yeah, that's kind of the seems that's the preferred solution at the moment. There are some constraints from Lambda function, as they said. It's like memory is limited. At least I think they refer to Amazon. Yeah, the AWS Lambda. So the memory and the package and the execution time is that's the kind, and it's only CPU. So if you want to deploy on GPU, it's not the option at the moment. Then they talk about the different model serving. So like Google TensorFlow's got the TF serving. Amazon on MXNet will have something similar, like model serving thing. And there's something from Berkeley, RiseLab. I think it's open source, Clipper. And some other solutions like Algorithma. But I did not use those as well, so I cannot tell a lot. Also in this course, they go very quickly through those. If you want to comment on those, just feel free to unmute yourself and talk more. Yeah, so then as a conclusion, they say if you want to do a CPU inference, you can do scaling like by launching more servers or using serverless system. Then again, deploying Docker files through Lambda is something they recommend. Yeah, and then if you want to use GPU for inference, then you would need to look at systems like TF, TensorFlow Serving, or Clipper. Then they moved on to monitoring. So once your system is deployed, you could monitor whether it's down, whether it's got any errors, what about the distributions, any shifts. Because basically, once your model is in production, you're going to get a little bit different data than you trained your model on. So it's good to keep an eye on things like error and stuff like that, whether your model is still performing as it was performing on the training and validation tests. And there are some tools that would monitor all those different things for you and create nice graphs. So that's what they showed there. And they talked about this Onix, this open neural network exchange format. So it's if you have like TensorFlow model and you want to exchange that to PyTorch model, you could use that framework. And there's many different frameworks that's you can do that. So you can Cafe2, Chainer, and other PyTorch, TensorFlow, and you can do that same with runtime. So I think I didn't use that as well, but that seems to be a nice way of if you work with different frameworks, you can use that to convert your models to such different models, different frameworks. Then they talk a little bit about embedded machine learning thing, but not that much again. And they talk about the different architectures that could be used on the mobile systems. So like the mobile nets, which they show difference between a standard approach when you have a 3x3 filter convolution and the mobile net. It uses, yeah, he was explaining that nicely, but I cannot now explain that the same way. But there's a link to that Medium post, which is supposed to explain this nicely. It's basically kind of makes this more simple. So it can be run on the hardware when you have less memory and then your processor is not that strong. So that's the whole thing. And on that graph, they show that these mobile nets can be scaled nicely as well. So it depends on your hardware you have. You can either make it smaller model or that have lower accuracy, or if you want better accuracy, the model will be bigger. So it's also a nice thing. And they compare that a little bit with the other systems like the G16 or GoogleNet or AlexNet. So as we can see, the mobile net is quite light indeed in terms of, I don't remember what the max was. I believe that's like number of parameters or number of computation that's needed to be performed for the model. And then from TensorFlow, there are some options like TensorFlow Lite or TensorFlow Mobile. And the Lite is like a more recent solution. There are some other tool frameworks, like from Apple, there is CoreML. From Google, there is MLKit. And the framework that's supposed to work with both systems, something called Fritz. And this also showed this NVIDIA embedded, I believe that was Jet something, but I'm not sure now. But this could be optimized to run on the FP16, and then you can perform that calculations faster. And that was the lecture 12. I know I did it very quick, but they also did it very fast, although they had more time. So do you have any comments or questions? I know for sure it was nice to learn about that stuff, but to learn more about this and do something in practice with that you need even more time. But at least for me, it was good to learn about all of that, the bigger picture about deep learning.
I'd just be interested, like in digging more into Kubernetes and even Docker. Like I don't use Docker, it's just the standard workflow. So personally, I sometimes like maybe later would love to play more with these.
Yeah, it's a lot. It's a lot to do, basically. But maybe it's worth doing. And then lecture 10 is actually the last lecture that is kind of from the course. After that, they have the guest lectures from Jeremy and from Richard. So we said those two are optional, so I'm not going to spend too much time on it, but the last lecture was the research directions. So they showed a couple of, let me open it. Yeah, so if yeah, sometimes those slides take some time to load. I'm not sure why. Yeah, so this lecture was about if you want to like explore something new in deep learning, where would you be looking to, like which direction? Because there's so many different ways you can take to explore deep learning. So this graph shows like how many papers on archive we have for kind of like machine learning. And we have, is it weekly or daily? 2016, 2017. That's per month. Look like this is, so one data point is 1 month. So we have about, that was 2017. There was about 2,000 papers per month. That's a lot. So he said basically no one can read that many papers. So he was like about to show in which areas at the moment seems to be the most work going on in deep learning. And then he was talking very briefly about those on the left and those on the right. He said this is also quite interesting, but then he wasn't spending that much time on. So like the few shot learning he talked about a little bit. So like he said, the supervised learning is very good, but it's a lot of labeled data and that takes a lot of time. So like this, in this example, he showed like for us, it's easy to find the difference between the hoverboard and the one wheel plus thing, even if we see just one picture. But for a deep learning network, that would be much more, you would need to show it like much more pictures of it. So he talked about the weight transfer, so the transfer learning, so you can use all the ImageNet embedded annotated images and then just use them and then transfer those to your model and then just only fine-tune your model, which works very good. But then there is a thing called the model agnostic meta learning, which he explained a little bit with using some math. So what I understood from that, instead of just, so like if you train a model on the ImageNet to the best as you can, and then you use those weights to your model to fine tune it, that's one way to do it. But the meta learning is a bit different. So in meta learning, you don't train the ImageNet, you don't train the model on ImageNet first so it gets the best score, but instead you train the ImageNet to such a way that it's ready for fine-tuning of your model. So it's like a different goal of that first pre-training, and that's describing those mathematical functions, which I didn't fully understood at that quick because I just watched that first time before the meetup. So basically, you're trying to find those parameters that will allow you to learn better once you fine-tune your model on your pictures. So that was quite interesting. I thought that, yeah, and then he showed some examples of that. And then he showed that indeed using that meta learning, you can get better, like lower test error than with the other networks. So that looks quite promising. Yeah. And then he was also showing this example on like regression example. So on the left-hand side, we have this meta learning, and then on the right, like pre-trained on all tasks. So like the standard like Fast.ai pre-trained model. So the red is the grand true, and then with the meta learning, we can get quicker to that unknown grand true with less iterations than with the with fully pre-trained, say, ImageNet model. So that was, I think that's quite interesting. I just wonder why it's not used more as such if it's got such good results.
I also think it's interesting, but do we know how that then works?
Yeah, so he kind of talked a little bit about that. So I didn't fully get details. The kind of intuition I got was that your first training, like if ImageNet is our example, we don't train our model on ImageNet on all images there and get the best result there on ImageNet and then transfer that to our model. We kind of use different metric for that. And this, I think this is the metric, the whatever that is, the function of that formula. And then and we stop there, and then we transfer that to for fine tuning. But I would need to dig more into that and to find out what exactly is going on there. But yeah, if I look at those examples, the green line, the green bar is always the lowest error. So seems to be performing well. And what I understood, you don't need to train on all data sets, so it should take less time as well. But there's a lot to read about that. So there's all that reading list if you want to master meta learning or maybe understand what's going on. There's some papers for us to read. So yeah, then he quickly moved on to, or maybe he showed some examples more about it. Yeah, but then he quickly moved on to reinforcement learning, as this also getting better and better. So this is a little bit different than the deep learning because you have the agent and you have the environment, and then your agent gets rewards depends on the action he takes or she takes. So that's how, on a big picture, how it works. And this started to show some good successes in like 2013, 15, playing Atari games, but then quickly beat human level performance. So beat Lee Sedol in a Go game. So Lee Sedol was the champion at the time, and there was a quite interesting documentary style movie about this. And Lee Sedol, when he was playing with the computer, he took this game so seriously, and that could be as well why he lost, because he was so nervous with this game. He was saying that he was playing to against computers to save humanity, something like that. He put himself in such a difficult position to to play, but and computer is without emotions, and computer was just playing. And I think Lee Sedol won 1 game out of 5, something like that. That was AlphaGo in 2015, and then they improved that model, calling AlphaGo 0 and Alpha 0 2 years later, and Alpha 0 beat AlphaGo, and now it's very good. So then OpenAI also creating this reinforcement learning bots playing in the Dota 2 game, and that I don't think they've managed to beat the best team, but they've managed to beat some professional level teams on the game. Some examples that I cannot show because there was videos, so it will not work here. And then he was talking about some improvements into that. I didn't fully understand that. He was also talking about the meta reinforcement learning. I'm not quite sure. I think he skipped those slides very quickly because he had also not that much time and he had a lot of slides. Yeah, he was showing an example here that on some models, in some situations, the model will not learn, and in some situation it will learn. I forgot what it was. If anyone remembers what it was, you can unmute yourself and talk about it. Okay. And then again, there's a lot of stuff to learn about reinforcement learning as well. Then he started talking about imitation learning. So when you don't have, I believe this is when you don't have too many examples of your training data, something like data augmentation. But I could be wrong here. He was showing robots here, so you can show to a robot like one example of where you drop a ball, and then the robot will perform that task. That was quite interesting, but I didn't get he didn't show all those slides as well. He was going very fast. Domain randomization, I don't even recall about that, so maybe he skipped that at all. Yeah, he didn't have a lot of time to talk about this at all. Yeah, then he showed this OpenAI. Again, I cannot show this. OpenAI, they make a lot of robots, or kind of like this is quite interesting. This robotic hand, it manipulates with this object. It looks like it was a human, so that was quite interesting. Unfortunately, the video doesn't work here. Yeah, and the next thing he moved on was the architecture search. So at the moment, so this is like Fast.ai. Jeremy would put that for us in the Fast.ai library. He would choose the best architectures like ResNet, and then he would put some default hyperparameters for us, and then we can just, with one line of code, we can train You can train like ResNet or something like that to a very good accuracy. But then this task is done more and more by automated systems. So we just throw data at it, and the system, through using brute force or some clever techniques as well, would perform a lot of calculations and will pick the best architecture. And I believe something similar to that will be to the Google efficient net, right? Maybe. I'm not fully sure. They didn't show that here, but Google just recently they published paper about efficient nets, and
I also hope to do a summary of it. Hopefully,
oh, you want to do it today? Oh, you okay?
No, not today. Next week for sure.
Okay, yeah. So so correct me if I'm wrong, but if I get it right, I think they used sort of AutoML to find out those architectures.
I believe so, yes, but I'll have to double check to be sure.
Yeah. So they've created this new network they call efficient nets, and that's on the right on this graph. And then we have all those networks that were created by kind of like by people as such. So like the ResNets. So on the x-axis, that's how complex the architecture is, how many millions of parameters, weights it's got. And then on the y-axis, how accurate it is. So you can see that this Google efficient net, at least on this benchmark, and I think that was ImageNet, it shows that it's the least complex, so that's good. It's going to run fast, and it gets the best accuracy of all, even like Inception or ResNets. So this looks quite promising. I've already seen people using those on Kaggle, so they're already pre-trained. I believe also pre-trained efficient net weights. Okay, let me go back to not sure what it was. I think this shows like some convolution layer architecture from 2012, and then technique called neural architecture search. I think he skipped all those slides. I didn't talk much about this. Then he was talking about data augmentation. I think those kind of, and also not only that, but also he was talking that you can make like different transforms of your data, but then also you can choose those that makes the biggest impact on your model and then only train on those. I think that was quite interesting what he said, but he didn't really go in depth on that. Then he quickly moved on to unsupervised learning. So the idea here is that we don't have labeled data to train on. So we want to learn from the data using neural networks. And there are many techniques. Again, he does very fast. I was not able to that quickly to understand everything that he showed. Yeah, like the GANs and stuff like that. And then someone created like from OpenAI, like so someone was able to, from the neural network, from the GAN network, someone was able to pick up those parameters that were able to like smile and age and stuff like that. So I think that's interesting. So it's already we can understand, because like the neural network is like a black box. So we're trying to understand more and more what's going on inside. So there's some progress already in there. We can understand which features already in a network are responsible for which feature for us as we see as humans. So the style transfers or the some other things. And the lifelong learning, I didn't get that at all. Maybe he didn't talk about this at all in this video. Or maybe he did, but very fast, very quick.
There's a question in the chat if anyone has tried domain adaptation technique.
Which technique?
Domain adaptation.
Oh. Sounds like not that many of us. So then when he was finishing, he showed like at Berkeley, the robot learning lab, what they have, like, so they have each PhD student's got like 4 GPUs per machine for local development, and then they spend some money on the cloud, but they want to get more GPUs and more money. So
Some paying $5,000 per month.
yeah. So this is kind of the resources they have. So it's kind of difficult to compete with them, but they're also smart as well, I guess.
Is the Boston lab different from this? I'm not sure about that.
I'm not sure as well. So then how to keep up, because we have so many papers per month, like 2,000 per month, it's difficult to read them all. So then he showed like some resources to help with that, like Import AI newsletter or Andrew Karpaty's archive Sanity. On Twitter, if you follow the right people, you will learn a lot about trends in deep learning, machine learning. There's a Facebook group seems to be very active. It's a shame I'm not on Facebook, but maybe I should create some fake account there and join the group. And also machine learning subreddit. So there's kind of resources that you could learn more.
Is there a single group on Facebook that we're talking about, or?
I don't know what this group on Facebook is. I don't really use Facebook, so I don't know.
I'm not active either, but I guess there are plenty of groups.
Okay.
All sort of AI, machine learning, deep learning groups.
Okay.
Facebook is the devil, and we should not use it.
Exactly. Same for Twitter, same for everything else.
Twitter's not too bad, I feel.
Like on Twitter, we have a lot of like interesting things about deep learning, but
yeah,
if you're not careful, you can spend too much time, way too much time on Twitter. So you have to limit yourself to follow only the right people, and maybe also limit time you spend on Twitter, because that can
They
take.
actually design a system such that it's addictive.
Yes.
They have actually neuroscientists working there such that
Yeah.
such that you get addicted to the social media stuff.
Yeah.
in my opinion, if you're careful enough, like it's a great place to stay updated for deep learning, and like if you follow the right people, you can always get a idea of what a good paper might be. Like if you see 4 or 5 people liking a particular tweet or retweeting it, then you have to check that paper out. That's how I go about it.
But is there a way at Twitter to, so say if you follow deep learning people and also someone else like sports or something,
Yeah.
is there a way to kind of switch?
Yeah.
Is there a way how to do it? Can you create like a list and then you only look at
Like you
it?
unfollow the people and you just keep the list. So whenever you want to check those details out, you can just go to your list and see them.
Yeah, because
that's actually a fairly important point. What papers to read and how to read papers, and I agree with Sanyam with the points he mentioned. We should use some sort of social filtering because, like Michael said, you get overwhelmed by this stuff. Like the output of papers, if you compare it to former times, it's just grown exponentially, and you need to imagine like a graph, right? So like Sanyam said, whom you follow on Twitter, they like a paper, then another person likes a paper, and so then it plops up on your feed by some sort of recommender system. And their Twitter can actually be helpful in the sense if they provide this sort of recommender system for us, let's say, and that's how I also do it. Like Sanyam said, papers that may be of interest to me plop up on Twitter, and so that's I think a good strategy.
Yeah, indeed. So that was as well. He said, yeah. He also mentioned it's good to join like a reading group. So if you have like 5 people, that's already 5 times less papers you have to read because someone can read that paper and only give you like a summary of it.
Divide and conquer everyone.
Yeah, that's right. I believe that was how to read a paper somewhere. Oh yeah, there is. So there's a guide from actually sources here on the slide, Gregory Kahn, about how to read a paper. So the how to read a paper sounds like it's a paper as well. It's a paper, how to read a paper. It's good. And that was it actually, I think. Yeah. So
Also important, I guess, is don't read every paper. Read
yeah.
the app. There's a reason there's an abstract and there's a title, right? So read the abstract, and then if you think the paper is, I don't know, not relevant to you, then don't read it. I mean, I've done that in former times that I thought, okay, all of these brilliant people out there have to read the papers. But a good tip is also, this might sound counterintuitive, but don't read every paper.
Yeah. I think another nice resource is the papers with code. So you get some sort of trending papers, but also what's nice with that, you also get code. So and mostly it's on GitHub, so you can access paper, but then you can replicate that. Where's the code? Oh yeah, it's here.
So I'm a grad student and I have to read a lot of papers. And in my experience, the best way to read a paper is kind of like you said, read the abstract, read the introduction, and then I actually don't read the results. I skim through the pictures, look at the pictures, try to read the legends and see if I can draw the same conclusions that they're saying in their pictures from their pictures, and then I read the discussion and then go back to the methods or results as needed if like the figures aren't enough info. But that's my way of reading papers, and it has made everything so much faster and easier, and I think you get to really critically understand where data is coming from and really like make your own interpretations, because sometimes they'll slap up figures and be like, oh look, it means a thing, and then you're like, no, it really doesn't. So
Are you talking specifically about machine learning papers? So what sort of figures are you referring to?
it kind of depends on just whatever papers. Like my background is primarily in biology, and so like I read a lot of biology papers, but I've also been kind of getting into sort of more computational biology papers, and so they do a little bit of machine learning as well. And so you can look at, instead of reading perhaps like the full architecture of like a machine learning paper, like, because in the methods they'll go through all the architecture and stuff. If you want to get just like a quick example or something, you can look at like the figure there. A lot of times they'll show like learning curves and stuff, or error rates, and then you can look at that and be like, oh look, does that actually make sense? And then you can dig back into the methods and see if what they actually did in the methods is what they're actually showing in their figure.
Got it. That's an interesting way. Thanks for sharing.
Yeah.
I think that's actually a very good strategy, right? Yeah. So
For sure. How I would approach is if I go to an abstract like Philip had mentioned, and I think even Sebastian Ruder had tweeted about this, that Jeff Dean had mentioned that instead of reading in depth through like breadth search, so just skim through as many abstracts and then dig deeper. So like I would check out an abstract of a paper, and if it looks interesting, I'll search for a paper summary of it. If not, I'll go ahead and create one. But usually I'll find a discussion on Reddit or maybe somewhere, see if that piques my curiosity. Then maybe go ahead and read the complete paper.
I'm pretty sure there's a paper how to read papers, but okay.
how meta.
Anyway, yeah, that was good discussion. Thank you for comments. Do we have Avinash on the call?
Yes, Michael, I'm here.
Oh, great. You okay to? Sorry, we didn't have time for you yesterday. Sorry, last week. But
yeah, no problem.
do you want to present today?
Yeah, sure.
Excellent. I'm going to stop sharing my screen.
Okay.
There's a question to N. I think that's their alias. So please check out the chart if you have. Avinash, please continue with your presentation.
Yeah. So am I properly audible?
Yep.
Yes.
And I hope you all can see the presentation slides.
Yep.
Yep.
Okay. Yeah.
Yeah, we can see it.
Okay. Oh, sorry. Is it full screen now?
No,
Or is
maybe
it
it's full
still?
screen.
If you go to present mode, maybe that'll be slightly better.
You have to click
I
on
did.
present. That's right.
Yeah. To select the proper one. 1 second. Yeah.
Sure. The screen share has stopped. Not sure if that's on.
Yeah.
Another thing that I was personally surprised was by when I was speaking with Dr. Goodfellow while doing the interview. Even for the interview, he's mentioned that he does not follow each and every development even inside of GANs. So, like if you can't keep up with all of the papers, I don't think that's a bad point. If that argument helps.
Also, I think now that we have a little time, Avinash, sorry, I need to say that real quick. Also, one strategy that I've used and I think is kind of good, textbooks kind of curate the basic knowledge for you. I mean, yeah, I'm the kind of guy, I think it's always important to go back to the basics, and like papers are nice, they're cutting edge research and so on, but there's a reason why people write Springer textbooks, for example. There, everything is nicely curated for you, and so that's another thing.
I could, Avinash, sorry for taking time. I could commit to doing
No
one
problem.
summary each week. I'll open up a feedback discussion. So if you have any papers that you want me to present first, after the efficient net, let me know. I could do a 5-10 minute presentation each meetup. That's about it from my side.
Also, I just skimmed through the statistical mechanics of Twitter paper that was mentioned in the chat. I think that's going to be amusing and kind of interesting. So,
Sure.
yeah. Sorry, Avinash. Now we take away your time. Now you can start. Sorry, this was just some digression from me.
No problem. Thanks for adding those points. So thanks, Michael, for your previous presentation and walking us through the lectures of full stack deep learning. So hi, everyone. I'm Avinash, and I'm currently working as an ML fellow in fellowship.ai. And in this presentation, I'll be giving an overview on model interpretability and visualization. If the things I discuss are already familiar to you, then please feel free to add anything you find useful. So here's the agenda that we have. And so the goal is to have an overview of deep learning, understand how these models are different from the regular algorithms, and walk through an example problem to visualize the inner layers of the network and the activation maps. So let's get started. So given enough samples of data, the deep learning models learn from the examples provided and automatically extract patterns that exist in the data, which in turn helps in performing various tasks. Example of some of these tasks include object detection, classification, speech recognition, language understanding, etc. The way we perceive things around us starts with taking inputs from the sensory organs, which get passed through several layered structure of brain by neurons. As we can see in the diagram here, deep learning models have a similar layered structure such that the representation learning happens incrementally, with each layer building on top of the layer before. So,
sorry, Avinash, I already have a question. Can you go back to the slide before?
Yeah.
the output layer, the output
Yes.
neurons, does one need exactly the number of kind of categories that one wants to classify as output neurons? So for example, if we wanted to do a binary classification, banana or not banana, we would need two output neurons, one saying banana and the other not saying not banana, and then the system sort of converges to one of these output neurons.
Yeah, so for binary, we can get it done even with a single neuron in the last layer. It's not that we need to. But normally, when we are doing classification, what we do is in the final layer, we have a dense layer which has the number of outputs which is equal to the number of classes that we have in the data. Like in case of cats and dogs, we'll have two. Like,
okay, so now I see how that works. Now I see how that works, because it's a threshold logic unit. The last
the
neuron,
softmax layer,
right? And right, and then it classifies based on that threshold. It says either banana or not. I can see how that. Would you say then that the last? I mean, I've heard people talk about like David McKay. I don't know if you've heard about him. He said that even like, if you think about logistic regression from statistics, logistic regression can be thought of as a single neural network.
Yes.
Because it makes sense to me, right? And you can converge to one output neuron and still classify two classes. Sorry for okay.
No problem.
Just made something click for me. I hope others have that experience too. But okay, thanks.
Yeah, feel free to ask any questions in between, please. Yeah.
I have the input layers, right? So this would be, for example, if we use image classification, these would be the pixels of the picture.
Yeah. So if it's like 299 by 299 resolution, that's what we'll be having in the input layer.
Yeah. Okay.
Yeah. Okay, let's go back here. So the deep learning models take some input, use the neural layers to process the input information, and give out some task-specific output. So even the traditional algorithms do the same as well, right? So on a very high level, yes, these deep learning models are very much like any algorithms we use to get the task done. The main difference between the two is how they internally process the data and operate on it. So let's quickly see how deep learning models differ from the traditional algorithms. Here we have an example of binary search algorithm. It takes in a list of numbers and a query item. We can see here that it has hand-coded logic, which works on the data and returns whether the query item is present in the list or not. As we can see, every part of the algorithm here is interpretable, and we can easily understand what the model does. Like, we know what the data is, how the algorithm is driven by logic, and what the output is going to be. So so far it looks good. Now let's pick another problem like this. So in another example, like activity recognition, given data like the speed at which a person is moving, the algorithm has to recognize the person's activity, whether it's walking or jogging or cycling or like that. So for a few possible outcomes, like recognizing whether the person is walking or cycling, the rule-driven approach or the logic-driven approach, which we saw in the previous screen, it works perfect. But what if we have another activity like playing golf and then playing cricket? So if these kind of more classes keep coming in, how can the logic-driven algorithm still work? So we can generate more rules, but we can see that the problem with this approach, it's clear. More complicated tasks ask for more and more rules. This isn't efficient, and it is also very less generic. So the black box we see here on the left is what differentiates a traditional algorithm from machine learning or deep learning algorithms. While the traditional algorithms take data along with hand-coded or developed rules, which is basically done by some developers, and it produces an output. Whereas the ML models take samples of the data along with correct answers. We are assuming it's for supervised learning here, and then uses this to understand the patterns in the data to automatically derive the rules, which means the core part of the task, which is understanding patterns that differentiate between different kinds of output, is learned by the model itself instead of the developer coding it himself or herself, like who or she is. So how do the neural networks manage to find the patterns in the data? How do they learn from existing data, and what do the inner layers of these artificial neural networks look like. All of this are studied under the field called model interpretability and visualization, which is currently a very active area of research. So this image here kind of gives an overview of what are all the things that we discussed here. In traditional programming, the input will be the data and the rules. Rules is nothing but the logic, and we'll be getting the answers. Whereas in machine learning, we have the data and the answers, and the rules are generated by the model itself. So to get an overview of what model interpretability is and why it is very critical, let's take an example problem. I'll be walking you through a food classification problem. The end goal of it is to build and train a model which learns how to recognize the type of food from the images. So if you have seen Silicon Valley, you must have come across this app called Hot Dog or Not Hot Dog. Basically, that takes an image and says whether the food in the image is hot dog or not. This is like the version 2 of it, where it not only says like what type of food it is from 101 categories. So the Food 101, it's a data set, and it has like 101 categories, and every category has 1,000 classes. So in total, this data from 101 classes. So we 750, like I said, 1,000 are the samples that we have for every class. 750 of them are taken for training and 250 are taken for testing. So let me open the notebook kernel. Yeah, so do you all see the Kaggle kernel?
Yes.
Yeah, we can see it.
Yep, can see it.
Okay, yeah. So here's the Kaggle kernel. It's on Food 101 dataset. And I used Keras and TensorFlow to work on this. We have the imports here, and this is the method to download the dataset. But since Kaggle already has this, I'm not running that here. It is commented out here. So the data has the Food 101 folder has these files. What we need are the images, which is a folder here, and we have a meta, which is another folder. So the images is the actual data folder. It has like 101 classes. Like in the case of cats and dogs, we have a folder, and inside that we have 2 directories called cats and dogs. So this follows a similar structure. We have total 101 folders here, like for one for every food type. And the meta folder consists of 3 text files. So train.txt file has the list of all image files which belong to the training set. And similarly, the test.txt has all the file names or the image file names which belong to the test set. So if you see here, the train.txt has something like this. So it says this is the image file name, and it belongs to the class apple pie. And now, so it may not be visible here properly, but this is just visualizing all the 101 classes of food here, picking randomly one from every class. And prepare data is the method that I wrote. Like, as I said, we don't have, we have all the data together. Like we have one folder called images, and inside that we have 101 folders, but the train and test split is not yet done. So using the train.txt and test.txt, I'm dividing the data into 2 folders, train and test. So that's the operation which is happening here. This is for training, and likewise, this is for test. So at the end of this step, what we have is the train folder has 75,750 images, 750 for every class, and we have 101 classes in total. And similarly, we have 25,250 images for test. So when I first got started with this problem, I started with training on the entire data. It's like 101,000 images. So every epoch on Colab or the VM instance that I had on GCP, it was taking 57 minutes or something like that, close to 1 hour. So instead of working on the whole data, I thought of getting started with much fewer number of classes. So I picked 3 classes. Instead of picking all the 101 classes, I got started with 3 classes so that I can do all the experiments. And once I have a model which is giving decent results, I can scale it up to more number of classes and see how the accuracy varies, or it gives me the same results. So here, these are all the, again, 101 classes that we have that are sorted. And now this dataset mini is the helper function that I wrote. Here, these are the 3 classes that I picked: apple pie, pizza, and omelette. What I'm doing is, from that original train folder, I'm creating another folder called train mini, which will now contain only 3 classes, which are these here, which are mentioned here. And similarly for test mini as well. So train mini and test mini are kind of subset that I created so that I can experiment with, I can run the experiments on. So here it is creating those data here. And now the train folder has only 2,250 images instead of 75,000 something. And the test folder has only 750 images. And I have used a pre-trained model on Keras Inception v3. So for this, I have referenced, you must have come across this blog on Keras, like building a classification model with limited data, where they used subset of cats and dogs and ran it for different settings, like using a pre-trained model, fine-tuning it, training from scratch, all of these things. So I have actually referred that blog and used the code from there, some of it. And so for data augmentation, I just tried rescaling, share, and some of these things. So here, since we are working on subset of data, the number of classes will be just 3. The training data folder will be train mini, and the test for the validation data folder or test folder will be test mini. And since Inception model will be expecting 299 by 299 resolution by default, that's what we have set for the image width and height. And here we have a train generator and validator generator. And so here comes the pre-trained model. And I'm taking the pre-trained model, and at the top of it, I'm adding a global average pooling layer, a dense layer, a dropout, and at the end, we have a dense layer here with only 3 neurons. So what Philip was asking a while ago. So since here we have only 3 classes, the final layer here, which is a dense layer, has only 3 neurons, and it's using softmax as the activation function. So this here we're compiling it. This is the kind of a standard procedure here in Keras. We have alternative for this in Fast.ai as well. So fit generator here is where the actual model fitting happens. It takes all the things like train generator, which keeps on, train generator is what picks our training data, does the augmentation, and then gives us these new images and different scaled images on the fly. And I have trained the model for 30 epochs. Prior to this, I actually ran for different pre-trained models and different number for other different parameters as well. So whatever we see here are the values which I finally decided to use. So at the end of training here, we have an accuracy of something like 95. So 95. So these are the 3 classes that we have again: apple pie, omelette, and pizza. And now this here we have the accuracy plot. We can see that it's done pretty decent. The reason for that could be some of the classes of some of the food classes that we have here already exist in ImageNet, which is the dataset on which the pre-trained model is trained on. So just for training for 10 epochs, it was giving, I remember, something close to 80 or 85% of accuracy. So the accuracy looks good, and even the loss looks good. So now what I did after this, so let's see some predictions. So I downloaded a few images here using wget and giving the image URLs. And
Sorry. Hi,
yes, please. Yes,
sorry to interrupt you at this point. I just had a quick question for the same. So go back to the code where you showed the different architectures that you used. So I wanted to ask, I mean, the architecture that you used to train the model. So I mean, did you try any other architecture, or what made you use this one?
I did. So I remember trying VGG and also ResNet. But from the experiment that I ran, Inception v3 was giving better results.
Okay.
When the other settings are unchanged. By just trying different pre-trained models, I found that for this data set, Inception v3 was giving slightly better results. That's the reason I used this.
Okay. I would be really interested to see, I mean, if we can use any other architecture, like instead of using global averaging pool 2D, what if or something like max pooling or something along the lines.
Okay, so if I'm not sure if I'm right about this, but for whatever that we'll be doing later on for model interpretability and visualization, I think there is some kind of a dependency with global average pooling, if I remember it right.
Okay.
Yeah, I'm not sure though. I might be wrong about it. I have to cross check that. But even I had, I mean, when I was reading through things for doing class activation maps and inner feature maps visualization, I remember reading somewhere that we need global average pooling layer.
Oh, interesting. I didn't knew that. Thank you so much. I will have a look at it.
Sure. I'll also cross check that. And once I have some info on that, I'll post it on Slack.
Perfect. Thank you.
Sure. Yeah. Thanks for the question. So going back, we downloaded the data here, and here we have a helper function which takes in a saved model, which is loaded. It takes an image list. It is converting that into an array. We're all familiar with this because whatever the transformations that we have done during training, the same has to be done at the time of when performing inference as well. So here we are scaling it down, and then we are doing the prediction. We are getting the index of with the highest accuracy, and we'll see the results here. So this is our input image, which is an apple pie. The title at the top is nothing but the predicted label. So it is an apple pie, and it rightly predicted apple pie. The same with pizza and omelette as well. So after training for 30 epochs, the model was able to get these predictions right. So it looks good so far. And now, as I said, so far we trained only on 3 classes, but this data set is like 101 classes. And in some of my previous experiences and some projects that I ran, I observed that we can't conclude when you have a data with 101 classes, by picking a subset of only 3 classes, you can't conclude that the model is going to do this, do well at the same level when more and more classes are added. So in order to cross-check that, what I did is, instead of 3 classes, I now picked 11 classes, which are these here. You can see how apple pie, beef capriccio, some classes here randomly picked. So now I trained the same model on 11 classes instead of 3. So we can see here the total number of training images are now 8,250. Previously for 3 classes, there was something like 2,000. And also for test images, we now have 2,750. When it comes to the model part, everything remains the same, except that the number of classes here and is nothing but 11, and the rest of the things remain same. The number of training samples will be increased, 8,250, and 2,750 will be the number for testing. So now we again training the same model. We are compiling it, and this time the best model will be saved with the name best model 11 class. And after training for about for 23 epochs, we see that accuracy, and we got an accuracy of 95 again. So it is pretty similar to what we got with 3 classes. So even by scaling up the number of classes to 11 from 3, using the same model, making no changes at all, we got an accuracy of which is pretty similar to what we got previously. And if we see the results here, so even here, these are all the 4 images that we picked: cupcakes, pizza, spring rolls, and garlic bread. And even here, the model got them all right during inference. These are the inference results again. So it looks good. We picked some data set and we trained a model. We see that the results are as expected. So does that mean that we are good to go? Can we take this model and put it in production or whatever that we have plans for? Again, a comparison, like when it comes to traditional algorithms, when you're getting the results that you have expected, it's more like your task is almost done. But when it comes to deep learning, it's not just enough if your model is giving you expected results. You should also know and make sure that it is doing it for right reasons and in the right way. So is our model really doing that or not? We can only know when we can look into the model. So model explainability, interpretability, and we have these things which are like an active area of research right now. So the way, as I mentioned in one of the previous slides, the neural networks learn incrementally. So to better understand that, let's take an analogy of how we learn to draw. If we have to like hand sketch the image of this dog here, we can't directly have on paper or a canvas the eyes or the snout or the mouth of the dog. In order to get there, we should first start with lines, edges, and we have to put together some lines, edges. A combination of these is going to give us more specific parts like eyes or ears. So that's what happens with neural networks as well. They start with patterns, like whenever you have a model, the first few layers are going to look for edges and some kind of regular patterns which exist in most of the data that we have. And further down the network, like the deeper layers are where we have features which are more specific to the data that we have. So this image is taken from a paper. You must be familiar with it. Even Jeremy has shown it in his lectures. So we'll see how this works. So we have a trained model which we are loading here. Here I have taken the best model of 3 classes, which I saved earlier, and I'm loading that model here. And we can see here, this is a summary. It lists out all the layers. We have inception. We used an inception layer, so it has something like more than 300 layers, which is why I have to, yeah. So these are all some helper methods. So the deep learning Kira's book is very, very good. I highly recommend that. It uses Keras, but all the things are explained pretty well. The code that you see here is directly picked from one of the notebooks of that book. So in the model that we have 315 layers in total. It is possible for us to visualize all the 315 layers, but since it's not possible to do that right now, we are here picking the first 10 classes, first 10 layers. So these are all the layers that we have. So these are the names. Look, so every layer can be identified by a unique name. So these are all the 10 layers that we picked to visualize. Con2D batch normalization activation, again followed by Con2D batch normalization activation. So what we do now is we have a model which we trained on our data, and we are now going to pick another image, a new image, or image which we already have. And we are going to pass this image through our saved model. And then we are going to pick the outputs of the first 10 layers, and we are going to visualize those. I hope that's clear. I think if not, this should help you. So show activations. So here activations are nothing but the outputs of every layer that we have. So here we can see that these are all the layers that we have. The first layer that we have is Cont2D. So what we see here, this first block here are the feature maps or the activations of the first layer, Cont2D, which has 32 filters. So each grid here represents the output of one feature that was used in this layer. So Cont2D, as I said, is a first layer in a neural network, which comes after the input layer. The Cont2D layer has 32 features in total, and each of these squares here represent the output of each feature. So as we can see here, these are like, we can still interpret that these are apple pie. Now let's just scroll down and compare the outputs of the first layer with that of the 10th layer. So as we can see here, this is the output of the first layer. Let me scroll on and show here. Here, this is the output of the 10th layer. So the main difference that we find between the first and the 10th layer is that the first layer is more interpretable as an apple pie. Whereas as we are further down, in the 10th layer, we see that it is less interpretable. So does that mean we are losing information? In a way, yes. But what exactly is happening here is that in the beginning initial layers, the model looks for simple edges and lines or patterns. That is why what we are seeing here are nothing but the outputs of vertical or horizontal edges that are detected, which is why we can still interpret that this is an apple pie. Whereas when we keep going down the network, the model is not going to look for simple edges and lines. It is going to look for features which are more specific to the data that we have. In this case, it is looking for more specific things that are related to apple pie, not just edges, which is why we see that the information, it gives a feeling that we are losing information, but it's not. It is trying to find more specific and low-level features which are related to that specific class. And also another thing to see here is that we have here these two sparse, these are called sparse cells, or the black cells that we see here. What's happening here is that the activation function that we're using is ReLU. This could be because whatever the feature that was used in this place, which is here, these two, they're not, then they have found some kind of negative patterns with the data. So as we know, ReLU ignores whatever the negative values or negative matchings, and hence this is kind of sparse. So we have them here, and we also have them here 1, 2, 3, 4, and this is, we are only visualizing the first 10 layers, and in Inception we have more than 300. So if we are going to visualize the layers towards the end of the network, we see more and more of these sparse or empty activations, and which is normal. Now this is for apple pie. Let's see how it looks for another image. Now this time we have another image, pizza, and we are passing that through our trained model and getting the outputs of the first 10 layers. Here again, we can see that the first layer, we can make out that it still looks like pizza, whereas the 10th layer, the same trend is observed. The visual information is being lost. And also we have the sparse activations here as well. We see them here, the black sparse activations. So this is one of the ways of looking inside the neural networks, where you can actually visualize the output of every layer. You can have an idea like how the input is being transformed from one layer to another, how it is changing, and what you can do about it. So this is one thing. Just to give you a clear idea, so this is how it looks. We have a pizza in Cont2D1, which is the first layer here, and Cont2D2 comes further down, and Cont2D3 is further far away. We can see how the visual information is being transformed. So this is just for showing the difference here. So what we have seen so far is activation map visualization, and there's another way which is called class activation. So what it does is, this will tell us what regions the model is looking for in an image to say that it's an apple pie. So this actually helps in understanding whether the model is trying to find the right features or not. So here, as we can see, this is the input image that we have, And this is the heat map that is generated. And when it's overlapped on the image, we see that to classify an image as an apple pie, the region that we have here, the highlighted, the colored region, that is what helps the model recognize that, okay, this is an apple pie. Let's check for a different image. So for a pizza, we can see that it has a totally different heat map or a different class map, activation map, class map. So the region here is totally different. So this is very helpful. Like if you have, especially when you are still experimenting with the data, you will know whether you have the right data or not. Like in one of the ongoing projects that I'm working on, we started with some amount of data and we were not getting proper results. And we didn't want to waste any time, and we quickly ran the class activation map code, and we got to see that the model is actually looking for regions of features which are not related to that class. So then we carefully went through the data, added more data, and then we saw that the model accuracy of performance picked up. So this is where class activation maps and class activations and activation visualization can come very handy. So besides these experiments, something else that I did is that, as you can see, we have a multi-class classification model, which means we have different classes, like 101 classes. What we don't have is, it's not multi-label. Like every image has a food which belongs to only single class. What I tried to do is, to the same model, I tried giving an image which has more than one food, like it has pizza and it has apple pie. So let's, this again is the same. This is not what I want to explain here. So if you see here, when we had apple pie here and a pizza here, and it predicted that it's an apple pie, right? And now what I did, I flipped it vertically so that apple pie, okay, here. So here we have pizza at top and apple pie at bottom. And I passed it through my model and it predicted that it's a pizza. And when I flipped it vertically, that I hope you can see the difference here. Here apple pie is at top and pizza is at bottom. And now it thinks that it's an apple pie. I know that the model is not trained to do multi-label, but still I just wanted to give it a try and see what the model does. So this is something that I noticed, like flipping the images, flipping the classes vertically has also flipped the result of the model. Like here, it said that it's a pizza, whereas here it thinks that it's an apple pie. This is when the flip was made vertically. When the same was tried horizontally, like here I have pizza and here an apple pie, it thinks it's an apple pie, and I flipped it horizontally. So, but when I flipped it horizontally, it doesn't change its result. It's still apple pie. So it could be because of data augmentation, or it could be something else. Something we might find out if we ran more experiments. I'm yet to do that. I'll be doing that once I have some time. So this is all about activation map and interpretability. So just to show you one example. So this is one example that I picked from a blog on the internet. Let's assume for a while that this model is actually trying to do person detection. There are two people, and based on what we see, we can see that it would say that there are two people, but something very important is missing here. The heat map shows that the model is not at all looking at the face as its feature. It is not even considering that, assuming that this model is trained to do people detection. So going through activation maps like these, we can train our model to give better results and better performance. And besides this, another very important aspect of model interpretability is bias. So we keep hearing a lot of things of bias. I don't think I have to repeat that. Just to give you examples, here's a blog which I wrote some time back. So in 2006, when someone on the internet searched for 3 white teenagers, they got images like this on right, like smiling teens. Whereas when the same person searched for 3 black teenagers, they got results like these, which are mugshots of black people. So, and then that is one thing. It is also critical. Model interpretability is so critical because it is being used in many use cases, even in law. So here is an example. There's a company called Northpoint, which gives some kind of risk assessment scores for accused people. Like if I'm accused and if I have a court case, this company is going to assign some kind of risk score saying the probability or chance of me doing another crime. So this was, I think this was done already some couple of years ago or something. So what it does is, you can see here the person on the left, that model or whatever the score that was generated, it predicted a low score for this person on left, whereas it predicted a high score for the person on the right, that she's going to, there's higher chances of her committing a crime. But when both of these people were released, it happened the other way. The person on the left actually ended up committing another crime, where the person on the right didn't do that. So bias is another problem which we can address using model interpretability and visualization. Bias is tricky because unlike the traditional programming where we have bugs which can be like found and fixed, bias is a much harder problem, which is what makes this area very interesting and good to work with. So yeah, that's what I had. If I'm open for questions now. I hope this didn't bore you all.
Hi, Avinash. No. This is Sagar here again.
Yes, Sagar.
Yeah. Thank you for the presentation. It was quite informative, and I really enjoyed it. So I have two questions for you.
Yeah.
Okay. I'll rephrase it. I have one question for you, and another maybe a checkpoint that I think would be valid. So the first question would be, you were mentioning something about data augmentation, right? Where horizontal flipping worked and the vertical flipping didn't work, right?
Yeah.
So I was just curious to know whether did you try anything relevant to TTA, like Jeremy once mentioned, test time augmentation is supposed to give results.
Yeah, so what I tried here got nothing to do with data augmentation actually. So TTI is something we can try for improving the model. I didn't do it yet. What I was simply experimenting here is that this model is only trained to do, it's not trained to do multi-label. What we have here is a multi-label input, which means it has more than one class of data. So this model is actually trained to work on images which have only one type of data. But at the end, I just wanted to try out, like, if I try to confuse the model with multi-label data, what is it going to do? So it was just a random experiment that I wanted to try. And when I tried it, I found that, So when I found that, so here, if you see, it thinks that it's a pizza, right? So when the same image is flipped vertically, the apple pie goes up and the pizza comes down, and then it now thinks that it's an apple pie.
Right.
Yeah. So I'm not really sure at the moment what really caused it. Is it some simple thing, or is it something else? As I said, I have to try more experiments on this. This thing is not observed when with the horizontal flip. The prediction remains the same even when the images were flipped horizontally.
Okay.
Yeah.
Okay. Sure. Okay. Now I get it. Okay. So quickly jumping to my second part. So so you mentioned something about the law.
Yes.
So I think a field called XAI, that's explainable AI, can be used to. I mean, it's also another hot field, as you mentioned earlier. So I think if a neural network predicts something like, okay, this person may commit a crime and this person doesn't, so I think XAI can, along with interpretability of a model, would help in providing more valid results. That's what
true. Yeah.
Okay, so are you doing anything along the lines of XAI too, or is it just interpret the model?
No, I'm not more into that. I have just I just work on these things with model interpretability and visualization.
Perfect. Okay. Yeah. Thank you so much. That was my question, and amazing presentation, man. Thank you so much. Learned a lot.
Thanks, Saga.
Yeah,
You
very good
mentioned the
presentation.
softmax function. Why is the softmax function used instead of for example, the logistic function?
Instead of logistic function. Yeah.
Yeah.
So it's like we are working with a classification problem where it's kind of a standard to use softmax, because softmax gives us kind of it actually gives us the probabilities. I think behind it will be using logits, right? Softmax.
Right. The logistic function gives us the odds ratio, and then in turn the probabilities. That's right. But it does the softmax. Basically, the softmax function has the same properties as the logistic function. So it ranges on the y-axis between 0 and 1. And
yes.
Yeah.
So even the softmax gives us scores which tell us, like if we have 3 classes, it's going to tell us what it thinks the confidence scores it outputs. So even that that totals out to 1. I think that must answer your question.
Yeah, just Wikipedia the softmax function, and I didn't understand but I have to read that up. I mean, the logistic function is sort of clear to me. You have this nice sigmoid sort of curve, and 1, 0, and so on. But it's a technical detail. I thank you very much for your presentation. I also think it was very, very interesting.
Thanks, Philip.
Also with model interpretability, it's like Saga mentioned before, kind of a hot topic right now.
Yeah.
I have a question.
Yeah, Michael.
Sure. So for me, it's kind of like, so this is the food classification, and classifies all those foods very, very nice. But
yeah,
what if you show now picture this model of a cat or a dog? Would that work still?
It will. That's the problem. It will still say that it would still. So the way it works is like Philip's question. We have a softmax layer at the end. So whatever the input image that we have, it is still going to say, okay, if we have a dog versus classifier, and we give it a tiger, it would still say that I think this is 30% dog and 70% cat.
Yeah,
it is going to do that. So I made a point for that at the end of this kernel here, for that, saying no class, right? So if the new image that we have given to the train model is something which is different from the data that it has seen, it would still say that it would still say with some confidence level that it belongs to one of the classes that it was trained on. So to avoid that, what we can do is, if we have cats and dogs, we can have another class, just name it unseen class, and put data coming from different kinds, which is outside cats or dogs. That way your model is also going to learn what a cat is, what a dog is, and also it is going to learn some of the things which will help it say that, okay, the tiger image might fall in the no class category, rather than saying that it belongs more to cat or dog.
Yeah.
Does that make sense?
Yeah. In fact, that's the thing. When I was doing exercises for
actually there are some papers on this. I didn't add them here, but I did come across those. One of the things is like to set a threshold. You can set a threshold saying that if none of my softmax confidence scores are above 60%, I'm going to say that the model, you can say that the model is not sure about what it's predicting.
Yeah.
Yeah,
and that makes sense. And my other question is, for example, if your model gets good predictions, and for example, if you have dogs and cats, and all the cats pictures are little kittens that are on people's hands, and then the model learns recognizing cats by hand.
That's there.
That's another issue, I think, with the classification.
I think that's the problem with CNN itself, right?
Yeah,
there are some problems. Yeah, so some of these are so even that, and also like even if you have an image where you don't have the entire face together, but you have cat eyes, nose, and mouth separately, the model will still think that it's a cat.
Yeah. right.
Yeah.
Hey, Avinash, great presentation. I have a question for you regarding the flipping that you experimented with.
Yes.
How do you generate the heat map on that? Is that a process going from input to output, or have you generated that based on the...
So to generate the heat map, so this is something which I got from the deep learning Kira's book that I mentioned. So they have a notebook where they actually explained the end-to-end thing, how to give. So we have a trained model which we saved, and from that we are passing our new image to that. And what we do, we are using. Okay, this is the code that is responsible for that part. Yeah. So here, if you see get attribution, and somewhere we have heat map. Yeah. Here, if you see. Heat map is so we have all these gradients, right? When you have a saved model, you have the gradients. So using those, and I think this is where I was talking about the global pooling comes into picture. If I remember it right, I'll be going through that and posting a more clear answer on this. But yeah, this is how it works. So when you give it the model here, it is going to load the new image that you have. And it is going to get the gradients, and it is going to generate the heat map for you. All that is happening here. Yeah. So
with your experiment, you basically, let's say both the images were, if I'm not wrong, 299 by 299, right?
Yeah.
So you squeeze both of them together to make it 299 by 299.
Oh, you're talking about this experiment that I did?
Yeah, the experiment. Yeah, the experiment part was it.
So this one, I just merged two of these images into one, and I gave that as an input. So the model during inference, it is going to anyway like reshape that to 299 by 299.
Right. So I'm just curious with the experiment that should you kind of squeeze the heat map too? Because I was just kind of looking at your heat map images, and they seem to be always grabbing, for some reason, the top part and not looking at the bottom part.
Yeah, if we see here, it is grabbing the top part. Whereas if it's, okay, you mean to say that it is always looking at the top thing?
I've just kind of observed, I don't know. And while you actually move your screen, there's a delay. So that's why I may be wrong on this, but this is kind of the thing that I observed. So I was just wondering.
Yeah, it could be. It could be that it could be something very simple or something that I've missed making changes. So that's what, but here if you see, for the horizontal thing, the heat map actually shifted. Here if you, I think it's visible here, it's on the right,
right.
This one, yes. And here we have it on the left side of it.
Yeah, right, okay. Yeah, so that's a cool experiment.
I'm not, thanks. I'm not really sure at the moment, like what exactly caused this, that I have to like try it with, like I have to run a few more tests on it. Maybe then I'll get to know. Yeah.
Right. Awesome. Thank you.
Thank you.
Yeah, it was great. Thank you.